standard. Am I audible to you?
Yes, ma'am.
Is this whiteboard visible?
Yes,
Yes,
ma'am.
ma'am.
Okay. I will share the PDF. A PDF is not like PPT. PDF is whatever the content I have written in the whiteboard is converted into a PDF. Okay. If you want, I will share it with you. Okay. It's not like a PPT. It will be the content of whiteboard. Is it useful? Aditya, do you want that PDF? Okay.
Yes, ma'am.
So, okay, whatever I have written in the whiteboard, I have converted that one into a small script, PDF script. I will share it with you. Okay. So today we are going to discuss about the data encryption standard. The first unit, the most important part of the first unit is data encryption standard. Okay. DES. It's a very first symmetric cipher. Okay. So DES is a first symmetric cipher developed by IBM. Actually, I think 2 days before I said it was invented in the year 1967. Sorry, it is invented in the year 1977. Okay, so 77 is the most important year in cryptographic perspective. In 77, DES was invented. The same year, RSA was invented. Okay, so the first symmetric crypto system developed by IBM, standardized by NIST. Okay, National Institute of Standards and Techniques, standardized by NIST. And the first attack against the DS was happened in the year 1997 by Shami, one of the designer of RSA algorithm. Shami launched the first attack against that DS algorithm. That itself, that is known as DS cracker, that takes 22 hours to break the crypto system. Okay, even probably 1 day is required to break the crypto system. Okay, and even that DS cracker is a hardware. You need to invest nearly 1 lakh amount to buy the product. Okay, so it's very costly. DS cryptanalysis is very costly. So still now we are using DS with a slight modification. Okay, so it was invented in 1977 based on the feature section. Okay, it is inspired by feature section. Most of the symmetric crypto systems are based on feature section. Okay, so that's why we discuss about the crystal architecture in the last two classes. That is based for all type of crypto system. In recently 2012, one crypto system was developed and standardized by NIST, that is IDEA. Okay, IDEA is also based on DES. IDEA is also based on DES. Okay, International Data Encryption Algorithm. IDEA stands for International Data Encryption Algorithm. That is also inspired by crystal architecture. Okay, but most of the symmetric crypto systems are breakable, but some few symmetric crypto systems are unbreakable, and one of the dominating symmetric crypto system which is unbreakable till now is variation of DES. Okay, so today's standard is we're using triple DS. Okay, TDS, that is triple DS is the today's standard. So understanding this data encryption standard is something important to understand the baseline architecture of all type of symmetric cryptography. Okay, so the DS is a block cipher. Okay? It works on, it's a block cipher. What do I mean by block cipher? Block cipher means, what do you
Encryption
mean by block
happens in a
cipher?
block of data.
Encryption, we can do the encryption and decryption on a block of data. Okay, the block always fixed. Okay, so this is this DES encryption algorithm. It takes encryption algorithm takes a block of data. Okay, the size is always fixed size. The plain text is a 64-bit binary. Okay, the output is encryption algorithm produces the output. The output is a ciphertext. Ciphertext is also 64 bits binary. Okay, and it takes another input. That input is a key. Okay, so the key of DS is lesser than the block size. That is 56 bit. Okay, so key size is 56. block size is 64. For example, if you want to encrypt 1024 bit block of data, you have to divide the 1024 bit block into fragments of size 64. Okay, and each 64 bit data to be encrypted by using this encryption algorithm. Okay, and it is also symmetric deterministic cipher. Deterministic cipher means as long as this P and K remains same, C also same. Okay, it's not a probabilistic cipher, so that it is not possible for quantum security. It's a deterministic cipher, deterministic algorithm. Encryption always produces the same ciphertext as long as the P and K remains same. Okay, so the equivalent decryption algorithm, it takes ciphertext as input, cipher block as input. Okay, text here is not alphabet. Okay, text is a binary block of data. So 64-bit input, it produces 64-bit output as a plain text, and another additional input required is a symmetric cipher, so it needs a key. Okay, same key, 56-bit key. Okay, so this is a architecture of DS algorithm. 64-bit input, it takes 64-bit input, produces 64-bit output. Additionally, it requires 56-bit key. Okay, and the detailed architecture of this DS is based on three major components. One is feature structure, feature structure, and second thing is it's a product cipher. So the same round to be repeated again and again. It's a product cipher, and it also exploits feature section. Also based on Shannon theory. Okay, it exhibits confusion and diffusion problem. Confusion, diffusion, both are possible. High confusion, high diffusion. So all these are the design idea behind this DS algorithm. In particular, it is based on feature section. Okay, and most of these symmetric cryptographies are implemented in hardware. Okay, because symmetric cryptography, it's not based on any arithmetic, any stuff called calculation. Everything is based on XOR operation and simply a substitution permutation. Substitution permutations are easily implementable in hardware just by using wiring. So DS is most of the DS algorithms are implemented in hardware. It's hardware compatible. Okay. So software point of view, it's additional overhead, but it's easily converted into a hardware output. Okay. So the DS, the input is 64-bit plain text. Okay, we start with this. The input is 64-bit plain text. Another input is 56-bit key. Okay, K, that is 56. Okay, ultimately what we require here, 64-bit output, 64-bit cipher output. Okay, in between some sort of processing to be exploited based on feature section. Okay, so the first thing, first I will prove that it is based on product cipher. Okay, so the 64-bit input passes through various rounds. Okay, so the DS algorithm is based on a fixed number of rounds, 16 rounds. Okay, 16 rounds. It's a product cipher with intensity or density of 16. Okay, 16 round and two extra rounds. Okay, that round is known as pre-input, pre-output. Okay, so what is the pre-input and pre-output? The first 64-bit data to be given to the first round. Okay, so this round is known as pre-input round. Okay, or another name for this is known as IP round, initial permutation round. IP stands for initial permutation. Okay, actually the design of this DS is very complex, but there is a reason for every action. Okay, there is a reason for every action. So the first round is the initial permutation round. Initial permutation round. The purpose of this round is DS. I said already, it's implemented in it will be implemented in hardware. Okay, hardware is vulnerable to one important attack called the side channel attack. Okay, so the hacker or intruder, if the hacker is an insider, then can able to access this hardware. Okay, by using the side channel attack, it is possible to break any hardware implemented crypto system. Okay, so to avoid that side channel attack, some sort of confusion or some sort of complexity to be added before the first round and after the last round. Okay, so that's why we have the DS designer have added IP round. IP round is not based on any key. Okay, no need to use key at all. IP is an initial permutation. Okay, so just to add some sort of confusion to resist side channel attack. I will tell you side channel attack later. To resist side channel attack, we need some sort of confusion in the beginning. That confusion should not be based on any key. Okay, so that the initial permutation is to provide resistance to the side channel attack. Okay, so if you make any confusion in the beginning, definitely the confusion to be removed at the end. Okay, so that's why finally we have another round in the features architecture. We have swapping. Okay, in a similar manner, we have IP inverse round. Okay, so this is known as pre-input rounds and this is known as pre-output rounds. Okay, the input to be directly processed to this initial permutation round, and after all the 16 rounds, the output to be processed by IP inputs. Okay, so this is known as pre-output. Okay, and this is known as pre-input round. Okay, so IP and IP inverse. So we have two rounds of operation. Then I said 16 rounds. So the output of IP is given to the first round. In the output of IP, in every round, it takes 64-bit input, 64-bit output. Every round is based on 64-bit input and 64-bit output. Okay. So here we have a round one, first round. Then the output is given to a round two or two, and so on. Finally, we have 16th round, as it is 16 round algorithm. So 16 rounds. Okay. As you know already, each feature architecture, in each round operation can be represented like this. Okay, the linear equation for this round operation, it will be like this: f of, okay, it's based on the previous right side component ri minus one, comma. It also based on another component called ki. What is a k? Ki is the sub-key. Okay, so each round to be associated with one input. One input is a previous round output. Okay, so the previous round output is one input. Another input also required, that is ki. Okay, so that's why this k, the actual k, it's given to the algorithm called sub-key generation algorithm. Okay, it passes through the sub-key generation algorithm. S K G, sub-key generation algorithm. Sub-key generation algorithm. And in sub-key, in DES algorithm, the key size is DES. The key size, original key size is 56-bit key. Okay, sub-keys. Okay, every round requires sub-keys. How many rounds? 16 rounds. So we have six. We need to generate 16 sub-keys. So the KI, the size of the KI not equal to 56. The size of the KI is 58. Sorry, 48 bits. Okay, so sub key size is 48, the actual key size is 56. Okay, so the actual input is k, the k will be converted or expanded into 16 48-bit data. Okay, 16 sub keys, each sub key of size 48 bits. Okay, so those sub keys are given to this function. So the first sub key is given to round one. I said already, IP and IP inverse is not based on any key. Okay, so R1 is based on first subkey K1. Okay, R2 is based on second subkey. Okay, R2 is based on second subkey K2. Okay, this size is 48-bit key, not 56. 48-bit key. This is also 48-bit. Okay, the last round is based on last subkey, that is K16, and this is also 48-bit. Okay, so the first high level diagram of D is this. Okay, very simple. It takes 64-bit input, 64-bit output, 56-bit key. Okay, second high level view of this is, in between we have 16 rounds. Okay, the plain text passes through the first pre-input round, that is IP round, initial permutation round, and it passes through 16 subsequent rounds, 16 homogeneous round. All the rounds are same. Okay, R1, R2, R3 till R16, symmetric rounds. Finally, the output of R16 is given to IP inverse. The final output is hypertext. Every round requires one subkey. That is output of subkey generation algorithm that takes K as input. Okay, so this is what the next architecture diagram of DS algorithm. Okay, so now to work out this DS, you need to know what is this IP and what is this IP inverse, what is this R1, R2, R3, and how this SK subkey generation algorithm works. All those things are required. Okay, so we get into one by one. Um, in asymmetric cryptography, encryption, decryption, two different algorithms. Okay, encryption is one process, decryption is a reverse process or inverse process. Okay, but symmetric cryptography, encryption, decryption, as you know, I think remember keys section. Decryption is not a separate operation. Decryption is the same operation, but the key to be applied in the reverse order. Okay, key to be applied in the reverse order. That's it. Okay, no separate architecture. The decryption process takes ciphertext as input, plaintext as output, same IP inverse, and passes through R1 to R16. So the first round should be based on K16. Second round based on K15. And the final 16th round should be based on K1. So only the order of subkey to be modified. Okay, so same hardware to be used for encryption as well as decryption. Okay, so nothing complex here. Clear? Okay. The first round is known as IP. Okay, so first I'll tell you how this IP round. In symmetry cipher DS algorithm, uh, it's not based on any arithmetic, not even simple addition. Okay, everything is based on substitution, permutation, and XOR operation. The key inclusions are based on XOR operation. Okay, all the confusions are exploited based on substitution. All the definitions are exploited based on permutation. Okay, so the first round is a permutation round. That is 64 bit to be permuted. Okay, so first I will get into the first round IP and IP inverse. Okay, what is that IP and IP inverse? How this IP and IP inverse is constructed? Okay, so it is implemented in hardware. So the wiring will be like this. Okay, the input will be the 64 port. Input port will be available. 1, 2 till 64 input port will be available. Okay, and 64 output port will be available. And the first port to be connected with one of the ports. Okay, second port to be connected with some port. Okay, so the permutation is an arrangement like this. Okay, the permutation is nothing but it's internal wiring. We have input port and output port. Input port, the appropriate input port to be connected with the appropriate output port. Okay, so that is based on a simple architecture by the DS designer. Okay, so first I will tell you the idea behind this IP round, how this IP round is implemented. All the DS algorithm, all the components are linear. You can linearly represent it. You can represent it by using the linear equation, except S box. Okay, X box is based on a completely random formulation, but other than S boxes, all the rounds, all the operations are based on linear equation. You can represent it by using a simple linear formula. Okay, so let me take IP round alone. Okay, so IP it takes 64-bit input, 64-bit input produces 64-bit output. 64-bit output. How this particular data is produced? Based on a simple lookup table. Okay, I can use all the diagrams. DS is based on so many different blocks. Okay, I can take the picture, I can paste it here. Okay, but if I follow that idea, definitely it is not possible to understand the linearity behind the design aspect. Okay, so that I'm going to write down this table again so that you can understand how the particular table is designed based on linear equation. Okay, so the data will be like this. One, the first bit to be shifted. Okay, 1, 2, 3, 4, 5, 6, 7, 8. Okay, you have to arrange like this. Then 9, 10, 11, 12, 13. Next is 16 bit of data. Next 8 bit of data. Then 17, 18, 19, 20, 21, 22, 23, 24. All these things, you have to construct all these table by yourself. Okay, if you are given with a DS problem, you have to solve it by yourself. So this design idea should be known to you. Okay, so 23, 24, then 27, 28, 29, 30, 31, 32. 30 bits are arranged like this. Then 48, then 49, 50, 51, 52, 53, 54, 55, 56, 57, 58, 59, 60, 61, 62, 63, 64. See, this is actually a table behind this IP round. What is the meaning of this table? That is the first bit, okay, the first bit, the bit 1, the bit 1 to be shifted to 58th bit. Okay, the bit 1 to be connected with 58th bit. Then the bit 2, okay, row major order. So the bit 2 to be connected with the bit second bit. Okay, so that should be permuted to the location 50. Okay, that bit to be permuted to the location 50. Then the third bit to be shifted to the location 42. Then the fourth bit to be shifted to the location 30. This is for the arrangement. Okay. Now this architecture is based on this table. Okay. Can you understand the linearity behind this table? How this table is constructed? So this is based on a simple linear formula. I will tell you the linear formula, but you should know the way in which the table is constructed. Okay. So this is a table. Based on this table, the wiring and arrangement to be constructed. Okay, the first bit to be connected with the 58th bit. The first bit is permuted at the 58th location. Second bit is permuted at the 50th location. Third bit is permuted to the 42nd location. And so on. Okay, I said this is initial permutation. Whatever the confusion we are doing, okay, whatever the confusion we are doing, that should be removed. Okay, that should be removed in the IP inverse. Okay, whatever the confusion, whatever the permutation we are doing, that should be removed in the IP inverse. Okay, and what is the meaning of this? Here, the first bit is shifted to the location 58. Okay, in IP inverse, what is expected here is in the IP inverse round, 58th bit to be shifted to the location 1. Okay, same thing. 50th bit of round 16 to be allocated to the to be shifted to the location 2 and so on. Okay, so this IP, whatever the action we performed in the IP to be removed in the IP inverse. Okay, so let's proceed with IP inverse. Okay, IP inverse. Okay, so IP inverse, we need to undo the effect of IP. IP inverse, it is used to undo the effect of IP. Okay, so IP inverse also takes IP inverse. IP inverse takes. Okay, I will also draw this wiring so that it will be understandable. Now here the requirement is input port to be connected with output port. The first bit, that is the first bit of output to be shifted to the location here. Okay, so this is nothing but this is 40th bit. Okay, so this one to be shifted here, the first bit to be shifted here. So we need to make the arrangement like this. For that, we need a different table. Okay, so this table also takes an input 64-bit input, produces 64-bit output. Okay, 64-bit input produces 64-bit output. Okay, this is also actually you need not undo the effects. This is also based on linear equation. Okay, let's go ahead with the linear equation. The input to be rearranged like this. Okay, just close this. This is IP table. And IP inverse table, IP inverse to be constructed based on a linear equation. Okay, so that will be like this: 1, 2, 3, 4, 5, 6, 7, 8. Okay, then proceed further: 9, 10, 11, 12, 13, 14, 15, 16, then 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32. Suppose 32 bit arranged like this, then the remaining 32 bit 33, 34, 35, 36, 37, 38, 39, 40. Then 41, 42, 43, 44, 45, 46, 47, 48. Then 49, 50, 51, 52, 53, 54, 55, 56, 57, 58, 59, 60, 61, 62, 63, 64. Okay, just check out this whether it undo the effect of IP. Okay, so just here check it out. The first bit is shifted onto the location 58. Okay, now here this is the location of the first bit. Okay, so we need to revert back in the IP inverse round this bit to be the first bit. Okay, so actually what is the position of this bit? In each row we have 8 bits, so 8 into 8 into 5, 40. So here this is actually 48th bit. So the first bit to be shifted onto the location 40. Okay, so second bit, where is the second bit? Second bit is here. Okay, so this is actually 8th bit. Second bit, it should be the 8th bit. In a similar manner, third bit, it should be in the location 40, and this is in the next row 48. Okay, third bit is in the location 40. Okay, and the fourth bit is in the location 60. So perfectly it is recovered. Okay, so actually the requirement is if the input passes through IP and IP inverse. Okay, for example, you have the input. If it passes through IP, okay, let us assume the input is X, it's 64-bit data X. Okay, if it passes through IP, you will get some inverse data. It's prime. Okay, when it passes through IP inverse, you have to recover back this. Okay, it should not be X double prime. It should not be something else. Okay, so it should undo the effect of IP. Okay, so this table to be constructed, these two tables to be constructed in such a manner that this IP inverse should undo the effect of IP. Okay, so IP inverse table, it should be the reverse table of this IP. Okay, so clear? Is this part clear to you? Can you understand this? And IP inverse is not based on any other component. It's based on only a 64-bit input. Just it takes 64-bit input and just do the permutation produces out. Not based on any key. But all these rounds are based on key. It also includes a key. Okay. So I can represent this round function like this. I have represented the round function like this. It takes two input. One is a right side component. Another one is key. Okay, so let's get into this R1, R2, R3, the round operation, or otherwise homogeneous round description of DES. Okay, so round operation takes one 64-bit input and one 48-bit input. Okay, just see this here. Each round takes 64-bit input, one 64-bit input, that is output of the previous round, and another input is a 48-bit. Okay, each round operation takes two input and it produces 64-bit output. Okay, let's get into the detail of this. Ri, not only R1, Ri, all the rounds are homogeneous. Okay, Ri takes 64-bit input, produces 64-bit output, and it also takes additional input 48 bits. Okay, let's get into the inner architecture of Ri. Is it clear? Can you able to follow me? Students, can you able to follow me? Shall we get into the next level of understanding? Shall we go for Ri? Any doubts so far? Am I audible to you?
Yes, ma'am.
Sorry. Okay, so let's go to the round operations. I think for round we'll take a new picture. Okay, because that is something important. The strength of the DES strength is based on security strength of DES is based on a round operation. Okay, so the round operation, each round we have 16 rounds. All the rounds are same. Ri, it takes two input. One is Ri minus one output, previous round output, that is 64 bits. Okay, and another input is Ki, that is 48 bit, and it produces the output. The output is 64-bit output. Okay, so confusion and diffusion to be exploited in each and every round. Confusion as well as diffusion to be exploited in each and every round. Okay, so this is designed in such a manner that confusion and diffusion to be exploited in each and every round operation. Okay, so how this? Let's take a simple detailed architecture here. So the input is 64-bit input. 64-bit input. First, you have to divide the 64-bit input into two equal half. Okay, so because it is based on pixel architecture. Okay, two equal half. Okay, so this part is known as a left side of 64-bit data, and this is right side of 64-bit data. And this is a detail of Ri, ith round. Let me take this is RIE, LI and RI. Okay, but the input is the previous round output. Okay, so the input is LI, RI minus one input, and this is Ri minus one input. The previous round data divided into two equal half, 32-bit and 32-bit. The first left side 32-bit is represented as Li minus 1. The right side 32-bit is represented as Ri minus 1. Okay, so this is actually a 32-bit data. Left side 32-bit data and right side 32-bit data. Okay, so finally we need to produce again two partition, left side and right side, just like a physical architecture, Li and Ri. Okay, and remember the physical structure. This part to be given to the round function. Okay, this part to be given to the function. Okay, so this is just 32-bit alone, and it takes another input. Okay, this input is 48-bit key Ki. Okay, and finally this result to be XORed with this. Okay, this result to be XORed with this, the output to be given here. Okay. So now this left side component to be directly filled by this. Okay. So left side is directly filled by this. Okay. So linear formulation is Li is equal to Ri minus 1 based on feasible architecture. Ri is equal to f of Li. I'm sorry. Because first we have to do the XOR operation. Okay. So Li minus 1 XOR. Okay, just to do it in the reverse side, this side. Okay, XOR with f of takes two more input Ri minus 1 and Ki. Okay, Ri minus 1 comma Ki. Okay, so exactly it's the feasible architecture. Okay, so Li minus 1, Ri minus 1, it will produces Li padded with Ri. Okay, so clear. Now you need to know what is this, how this function to be implemented. Okay, it is based on feasible architecture. The success is in the design aspect of this function. Okay, so just to closely look out this function. Okay, I'm going to detail this function now. Okay, what about this function? This function f, okay, it takes two input. What are those? The first input is a 32-bit input. Okay, it takes 32-bit input. Okay, it takes this array minus 1, that is 32-bit input. Another input is a 48-bit input, that is ki, 48-bit input. And what will be the size of this? This is also 32-bit. Okay, it produces 32-bit because this is XOR operation. XOR operation is a binary operation. It takes equal length input. So this is 32-bit input output. This function f, it takes 32-bit input from the previous round, Ri minus 1, produces 32-bit output. In addition to that, it takes 48-bit key. Okay, so I can represent like this. This is 32-bit input, 32-bit output, and 48. Okay, so let's go to this architecture, the detail of this. Okay, how this function is defined. Clear? Is it clear? Shall I proceed? Students?
Yes, ma'am.
Okay, now get into this function alone. Okay, this diagram, I will write it out here. I use this push. I think this is better. So this function f takes 32-bit input. Okay, 32-bit input. That input is 32-bit, produces 32-bit output. Okay. So the first operation, this is actually a detail of f function. Okay. So the first operation is the 32-bit data to be expanded into 48-bit data by using one box called expansion box. Okay. So this box is known as expansion box. Okay. Expansion, cryptographic expansion. Okay. This box to be expanded. Oh, so the 32-bit data to be expanded by using expansion box. Okay, this box is known as E box. I will tell you what is that E box, how it works. Okay, this is purely a permutation box. So the output after expansion, this E box, the E box will produces 48-bit data. Okay, E box will produces 48-bit data. Now, in the function f, I will get this input. This is a 48-bit key. Okay, that is simply XORed here. Okay, that 48-bit is XORed here. That 48-bit key, ki. Okay, this is Ri minus 1. That 48-bit is XORed with this 48-bit input. Okay, the output of the expansion box is simply XORed with the ki. That's it. Okay, but after that, this one to be given to the compression box, cryptographic compression box. Okay, so cryptographic compression box, it will be like this: compress the data, reduces the data. How? that is based on another box called X box. This S box takes 48-bit input, produces 32-bit output. Okay, now observe this. This is a compression data expansion box, and this is known as compression box. Compression box. Okay, here the expansion box is known as E box. E box takes 32-bit as input, 48-bit as output. Compression box is known as S box. S box takes 48-bit input, 32-bit output. Clear? Is it clear? So, to provide still more better confusion, the output is again given to another box that is known as permutation box or P box. Okay, P box produces 32-bit input and 32. It takes 32-bit input and produces 32-bit output. Okay, so altogether, this is a function of this. Yeah. Okay, function of this. Yeah. This is a F box construction. It takes 32-bit input, 132-bit input, and 48-bit input, produces 32-bit output. Based on F box is based on three different input functionalities. One is E box, cryptographic expansion box. Another one is cryptographic compression box, S box. And still, to increase further confusion, we have one more box, P box. Okay, so this function is based on three more linear equations: E box, S box, and F box. Okay, E box, S box, and P box. Okay, E takes 32-bit input, 32-bit input produces 48-bit output. Okay, S box takes 48-bit input, produces 32-bit output. Okay, P box takes 32-bit input, produces 32-bit output. Okay, so the idea behind these boxes are also linear equation. Okay, I will tell you how this S box, E box, P box are constructed. Okay, so every round is based on three more substitutes, three more lookup tables, say three more connectivity. One is E box, another one is S box, third one is P box. E box and P box for diffusion and S box for confusion. Okay, confusion, that is breaking the relationship between the key and the ciphertext by S box. Okay, diffusion by E boxes and P boxes. Okay, so every round Shannon theory principle is exploited, so it produces confusion and diffusion. Okay, so shall we proceed with E box? Is it clear? Shall we proceed with E box? If any one of you
Ma'am,
respond to me, then I will proceed. Yes.
ma'am, can
Yes,
48
tell.
bit be converted to 32, ma'am?
Yes.
Will there be any loss in data?
That is what. Very good. Very good question. The 32-bit expanded to 48, 48-bit expanded, compressed into 32-bit. Okay. That is the design of the entire DS algorithm. The strength of the DS algorithm is based on the construction of the S box. Okay. Without losing even a single bit, it reproduces the data. Okay. S box is constructed in such a manner that it won't lose even a single bit of data. Okay.
Okay, ma'am.
Shall we proceed with the E box? Expansion
Yes, ma'am.
box?
Yes, ma'am.
Actually, you have to think like that. For example, if you want to design your own crypto system, because at the end of this course, cryptography and network security, definitely you can understand the way in which the cryptographic algorithms are exploited in various applications. That's possible. That's good. Okay, that's a basic understanding. But what is a high level understanding from this course? You can design your own crypto system like DS. You can design your own crypto system like AES. Okay, that is the ultimate requirement of this course. Cryptography and data security. It not only provides the applicability of all those basic cryptography component in various fields. Okay, now I think you can understand this DS is a hardware, so you can encrypt your hard disk content or storage content by using DS hardware. That is good. But how this algorithm is designed? What is the design aspect of this algorithm? That should be, you need to understand that one, that idea. Then only you can design your own crypto system, your own basic symmetric crypto system by exploiting these properties. Okay. So if you want to publish any paper or if you want to do any research in cryptography, that is very simple. You have to understand the design aspect of successful crypto system. Just to incorporate small changes with some common sense, then automatically it produces a better system. Okay, or equally good system. That is what the idea here. So what is a E box, S box, and P box? So E box is an expansion box that is based on a simple linear component. Let's get into this. Okay. So let's go to the E box. Okay. Each function is based on three different boxes. The first box is a expansion box, E box. Okay. So E box, it takes 32-bit and produces 48-bit. Based on very simple principle, the 32-bit data are divided into fragments of size 4 bits. Okay, the first 4 bit, second 4 bit, third 4 bit, and so on. Okay, and these 4 bits are, each 4 bits are expanded into 5 bits. Okay, each 4 bits are expanded into the, sorry, not 5 bits, 6 bits. Okay, so how this, these 4 bits are used for the in between 4 bits. Okay, the first bit and the last bit will be the duplicated bit. What is the duplicated bit? Okay, this bit, this will, this bit to be copied from the first bit of this. Okay, and this bit is copied here. Okay, so all these are like I said, all these are like wiring, input port, output port. Okay, so some of the bits are duplicated based on a simple table. Okay, I'll write down the table so that you can understand this. The input is 32-bit input. First arrange the 32-bit input. Okay, first you have to arrange the 32-bit input like this. The first bit, second bit, third bit, fourth bit, then 5. Okay, this is first bit, second bit, third bit, fourth bit. 1, 2, 3, 4. And this is 5, 6, 7, 8. 5, 6, 7. I said you have to represent the data in terms of fragments of size 4. Okay, the first 4 bit, second 4 bit, and so on. Okay, so 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32. Okay. The data to be divided into fragments of size 4. Okay. So the first 4 bit, second 4 bit, finally the last 4 bit will be like this. Last 4 bit. Okay. So this will be 29th bit, 30th bit, 31, 32. Okay. Now some bits to be added. Actually, in this E box, the 32 bit to be expanded into 32 bit to be expanded into 48 bits. Okay, that means we have to add 16 more bits, 16 more bits. Okay, so now we have to add like this. This fourth bit and fifth bit to be duplicated. Okay, now it's very simple. Here, just I'm going to show the added bit. This bit, the fifth bit here, the fifth, this fifth bit. What is this? That is exactly 5. Okay. So the one more bit is added, that is duplicated 5th bit. Okay. So here the bit is added, that is duplicated 9th bit. Here 12th bit, this will be 13, after 16, 17, then this will be 21, then 24, this will be 25, then this will be 29, then after 32, circular shift. Okay, that the bit will be the first bit. So 8 bits are expanded like this. Okay, just I'm showing only the suffix bit. The suffix bit is nothing but the next subsequent bit. Okay, the first fragment, the suffix bit is a 5th bit. Next fragment, the suffix bit is a 9th bit, this bit. Okay, and so on. But that will create only 8 extra bits. But 8 more extra bits are required. So 8 more extra bits are based on prefix bits. Okay, the prefix to 1 is nothing but 32. Okay, the prefix to 5 is nothing but 4. The prefix to 9 is 8. Okay, so this will be 12 and 16, 20, 24, and 28. Okay, so the prefix and suffix are expanded like this. So what about this? The first bit is copied here. This bit will be the 32 bits. Okay, and here the first bit, not this, the first bit will be the previous bit, that is the 4th bit. The last bit, it will be expanded like this. Can you understand this? So these are extra bit padded, duplicated bit. Okay. So the 4 and 5 are duplicated twice. Okay. 8 and 9 are duplicated twice. 12 and 13 duplicated twice. That's it. Now check it out. The first bit will be the 32 bit, 32nd bit. Second bit will be the first bit. Okay. So this will be 32nd bit, then first bit, second bit, third bit, fourth bit. Now this will be fifth bit. Now this is again fourth bit. This will be 5, 6, 7, 8 and so on. Okay. Now this will be the expanded 48-bit data. Altogether we have 48-bit data. Clear? Can you understand this? E-box?
Yes, ma'am.
Okay. So it's very simple like this. But the next is a substitution box, S box. Okay. S box is slightly complex because the entire strength of this DS is based on S box. Okay. So what about the S box? S box takes, it's a compression box. It takes 32-bit input, produces, sorry, 48-bit input, it produces 32-bit output. Okay. Takes 48-bit input, produces 32-bit output. Okay, so not only with the DES, AES, IDEA, all ciphers are based on a technique like this. Okay, definitely there will be SBox in all ciphers. AES is also based on strong SBox. Okay, IDEA is also based on a strong SBox technique. Okay, SBox is a substitution box. It provides better diffusion. 48-bit input produces 32-bit output. Okay, in DES algorithm, all the components are linear. E-box, P-box, IP round, IP inverse round, sub-key generation round. All the components are linear. You can do it by yourself. Okay, but Xbox is not linear. It's based on pseudo random number generation. Okay, so this Xbox is constructed based on a probabilistic method. Okay, now DS is based on 8 S-boxes. DS is based on 8 S-boxes. Okay, each box, let's take one box, S1 box. Each box is based on uh, 4 rows, 16 columns. Okay, 1, 2, 3, 4. It has 4 rows and 16 columns. 1, 2 till 16 columns. Okay, how this S boxes are constructed based on pseudo randomness. Okay, the first requirement here is each column should be unique. Okay, totally we have 8 S boxes, S1, S2 till S8. Okay, so all the boxes are based on this structure, 4 rows, 16 columns. Okay, all the columns are unique, all the rows are unique, all the rows are unique, all the rows are unique. Okay, and each row, a value appears 1 to 50, 1 to 16, the value appears only once. Okay, in each row the value appears only once. The values between this range appears only once. Okay, and one more design aspect of this box is each box is also unique. S1 is something different, S2 is something different, S3 is something different. Okay, so I will show you that box here. Okay, can you able to see this box here? Otherwise, I will show it out with. Okay, just to say these boxes, we have 8 boxes. In cryptography, in CAA as well as in the university examination, you will get only analytical type question. You have to solve the problems. Okay. For DES, you will be given with a 64-bit input. Okay, you have to produce a 64-bit output. Maybe sometime they may ask you to compute a single round output, or 2 round output, or 3 round output, maybe anything. But this will be the supplementary material for DS. Okay, because these boxes you cannot generate by yourself. All these boxes are designed by the designer. Okay, so this is a box one, S1 box. Okay, see this. We have 16 column and 4 rows. Okay, check it out. The column, each column is unique. Altogether, each boxes are unique. Okay, the first column, first row starts with 14, 4, 13. Okay, that row is completely unique based on pseudo random number generation. A cryptographic pseudo random number generation methods. So there are so many cryptographic pseudo random number generation methods are available. The DBS algorithm, quadratic residue based pseudo random number generation, so many algorithms are available. So the pseudo random number generation functions are applied here to construct this. But which particular pseudo random number generation function is used, that is hidden. Okay, still now it is hidden. Okay, so to solve DS algorithm, this will be given as a supplementary material. This will be given as a supplementary material. So there are 8 boxes. Okay, so how this S box lookup table to be used. Okay, I will complete within 2 minutes because I have started this S box. Let me complete it. The input will be S box. What is it? The input is uh, 48-bit input. It should be converted into 32 bits. Okay, how? First of all, we have to convert this 32-bit data, the 48-bit data into the fragments of size 5 bits. Okay, the first 5 bit, second 5 bit, the first 6 bit, second 6 bit, third 6 bit, and so on. Okay, the 48-bit data to be divided into fragments. Okay, each fragments of size 6 bits. Then how many fragments are possible? How many fragments? Divide the 30 to 48-bit data into 8 fragments. That's why we have 8 S boxes. Okay, the first fragment to be given to S box 1, S1 box. Second fragment to be given to S box 2. The third fragment to be given to S box 3. That's why we have 8 different S boxes. The purpose of 8 boxes are 8 different S boxes because you have to process each fragment separately. Okay, what is a fragment? The fragment made up of 6 bits. Okay, so the let us consider the bit like this: 1 0 0 1 1 1. Okay, let me take a fragment like this. Okay, these tables are these S boxes to be used as a lookup table. How? Let's take this bit, this first bit, and this bit to be used as a row ID. Okay, to be used as a row ID. Okay, 0 1 0 1. Okay, 0 1 means 0 0 0 1 1 0 1 1. Okay, that is a row ID here. 0 1 means the first row, this row to be used, row number 1 to be used. Okay, and the in between 4 bits used as a column ID, that is 0011. 0011 is used as a column ID. Okay, starts with 0. So 0 1 2 3. Okay, this value will be considered as output. All the values are between the range 0 to 15 only. Okay, we can represent in terms of 4-bit binary. So the 4, the equivalent output will be 0 1 0 0. So 0 1 0 0 1 1 to be converted into 0 1 0 0. Similarly, the S2 box to be applied. The first bit and last bit together form row ID. In between 4 bits together form column ID. The subsequent the intersecting element to be replaced. Okay, clear? Is it clear? So each fragments are converted into 4-bit output. The first fragment converted into 4-bit output. Second fragment converted into 4-bit output. Altogether 8 into 4, 32-bit output. Clear? I'll stop here. We continue with the remaining component later. We have completed part of round function. Each round function is made up of 3 boxes: E box, S box, P box. Okay, we have completed expansion box, substitution box. Okay, we continue with the permutation box tomorrow. Okay, that part is hidden, and we continue with the sub-key generation round and all those things. Okay, I continue DS tomorrow. Any doubts so far?
Ma'am, can you repeat the fragmentation to output generation, ma'am?
I'll tell you. I'll tell you. Let me take the first, the 32-bit output. It will be like this: 1 0 0 1 1 1 1 0 0 1 1. Some 48-bit data. Take out the first 6 bit to form the first fragment. I have taken 1 0 0 1, the first 6 bit. Okay. In this first 6 bit, the first bit and last bit to be used. So first bit, first bit in another. Oh, sorry. First bit is 1, last bit is 1. Okay. So the first bit and last bit, the used as a row ID. Okay. So just to form first bit and last bit to be used to form the number 1 0 0 1 1. The first bit and last bit, that is 1 1. Okay. And in between 4 bit, that is 0 0 1 0 0 1 1. 0 0 1 1. Okay, so my input is, the fragment input is 1 1 0 0 1 1. So this is used here, and this bit and the last bit used to form this. Okay, so this is used as a row ID, and this is used as a column ID. Okay, so for this row ID, I can write like this: this row is 0 0, and this row ID is 0 1. The second row ID is 1 0. The last row ID is 1 1. Column ID, this will be 0 0 0 0. Okay, and this will be 0 0 0 1, and this is 0 0 1 0. Finally, this will be 1 1 1 1. Okay, now take it out row ID 1 1. So now this row to be used here, and column ID is 0 0 1 1. So 0 0 1 1, this will be here. Okay, this value to be replaced. This, I think I did mistake. That's why you asked me to repeat. Am I correct?
No, ma'am. No, ma'am. I didn't understand,
Okay,
ma'am.
so I'm sorry, sir. Okay. So the in between 4-bit used for column ID, and the first bit and last bit is used for row ID. Okay, here the first bit, last bit together forms 1 1. Okay, that row is indexed, and the column is 0 0 1 1. That column is indexed. The intersecting component is what is that value? 2. Okay, so the final output will be 0 0 1 0. 0 0 1 0. Similarly, this is for the first fragment. Take it out the next fragment, 1 and 1, 1, 1. So the last row to be used, 1 0 0 1, the column number 1 0 0 1 to be used. I think this is 1 0 0 1. Am I correct? 1 0 0 1, and this number to be replaced. 7. It is 0 1 1 1. Am I correct? Is this a column number? 0 0 1 1. You just proceed with and find out appropriate column number. The column number 1001, the column. That column, the intersecting value to be used. 6 or 7 ada. So the subsequent fragment, the third is box to be used. Clear?
Okay, ma'am. Yes, ma'am.
So we continue with the P box and other component too. Okay. Any more doubt related to this? Any more doubt? I'll stop here. If you have any doubt, please post it in the GCR.